some basics here, and I imagine there's some people in the audience who don't really have a good grip of what the backpropagation algorithm is. So I'm actually going to explain that very briefly, so you know what we're talking about. And then I'm going to show a few examples of what it can do. And these are all things that are now a little bit out of date. So if you want a computer to do something, the old way to do it is to write a program. That is, you figure out how you do it yourself, and in exquisite detail, you tell the computer exactly what to do. And the computer's like you, but faster. The new way is you tell the computer to pretend to be a neural network with a learning algorithm in it. That's programming. But then after that, if you wanted to solve a particular problem, you just showed examples. So suppose you want to solve the problem of, I give you all the pixels in the image. That's 3 numbers per pixel for the color. There's, like, let's say 1 million of them. And you have to turn those 3 million numbers into a string of words that says what's in the image. That's a tricky program to write. People tried in AI for 50 years and didn't even come close. But now a neural net can just do it, and I'll show you how it does that. That is, we have no idea how to write that program, but a neural net can do it. So we're going to make our neural net out of artificial neurons. An artificial neuron is going to have some input lines that come from the sensors or the neurons. On each input line, there's going to be a weight that could be positive or negative. And it's going to adapt by changing the strengths of those weights. And the way it behaves is that it takes the values on the input lines, multiplies each value by a weight, adds it all up, and that's its total input. And then it gives an output that's a nonlinear function of that total input. And the function is shown on the right. If the total input isn't big enough, it stays silent. As soon as the total input gets bigger than that, it starts giving a response that gets bigger as the total input gets bigger. For 30 years, we used a different kind of neuron that didn't work as well, and then we tried this one, and this works better. That gives you some idea about the state of the art in the field. There's very simple changes that just make things work much better that people haven't explored. Okay, we're going to hook those guys up into networks with multiple layers. And we're going to learn the connections on the inputs to the neurons in all the layers. And so the problem's solved now. All we need to do is figure out how to adapt those connections, and we're done, because these networks can do anything. So it's just a question of changing the connections. And there's a very interesting and simple algorithm that occurs to anybody who believes in evolution, which hopefully is most of you. What you do is you take one of the connections, you take a small batch of training examples, a typical batch, you run it through the network, and you see how well the network does. So how similar are the outputs of the network to the outputs that you think are the correct answers on this training data? And then you change that one weight, and then you run this batch through again. And you see if that improves things. If it improves things, you keep the change. If it doesn't improve things, you don't keep the change. You leave it like it was. That's it. And that algorithm works. That's a very naive view of evolution, but it works. It's only mutations you're doing. And if you just do that long enough, you'll get a network that does good things. The problem is that I have to run a whole bunch of examples through the network, actually twice, for each weight, and I might have 1 billion weights. So what we want to do that algorithm. That's the basic algorithm. You're going to tinker with weights and just keep the tinkers that change. But it's hard to do it efficiently. And so we're now going to use some calculus and do the same thing efficiently. What we do is, because we know the weights in the network, or your brain knows the weights in your brain, we don't actually have to tinker with a weight and see the effect. We can imagine tinkering with a weight and figure out what the effect would be. If you know all the weights in the network, you can say, if I were to change this, the output would change this way, and that would be good. So therefore, I want to change this. So what we can do is look at the discrepancy in the output, and from the discrepancy between what we want and what we got, we can send information backwards through the net that's doing this computation for every weight of how a small change in that weight would affect the output, how a small increase in that weight would improve or make worse the output. And we can do that for all the weights in parallel. So in the same amount of time as the mutation algorithm can figure out what to do with one weight, we can figure out what to do with all the weights. And if there's 1 million weights, that's 1 million times more efficient. And 1 million times more efficient is enough to make a difference. And backpropagation had great promise. But by the 1990s, people in machine learning had given up on it because they had relatively small data sets and other algorithms worked better. And what's more, you could prove things about these other algorithms. With backpropagation, you couldn't prove it would work. And what's more, when different people ran it, they got different answers. And so if you're obsessed with there only being one correct answer and you're being able to prove you get it, backpropagation is not for you. Nor is life, actually. One of the reasons people lost interest is that it doesn't work so well. The naive algorithm didn't work well in deep networks, and it didn't work in recurrent networks, which I'll explain in a minute. So then a few technical advances were made in Canada. By Canada, I mean Toronto and Montreal and New York. And we're very concerned about those details of those advances, but that's minor for everybody else. The main message is if it gives you a lot of labeled data and a lot of compute power, backpropagation now works amazingly well. And the rest of the talk will be trying to convince you of that. So here was the first practical problem that it made a big impact on. That's not quite fair, but since this was done in Toronto, I'll pretend it was the first. Actually, for handwritten digit recognition, it made a big impact. But people said that's an easy problem, whereas speech recognition is a tough problem. So a couple of graduate students at the University of Toronto took an algorithm that I'd been working on and applied it to speech recognition. And you take some coefficients that describe the sound wave, you put it through multiple layers of hidden units, and these were lots of hidden units. So there are only a few million training examples, and between each pair of layers, there's 4 million parameters there, because it's fully connected. So a statistician, if you do statistics 101, you will know that this cannot possibly work, because there's many more parameters than there are training examples. So it's crazy. If you want to critique statistics 101, you might say, in your lifetime, you make about 10 billion fixations, and you have about 10,000 times more synapses than that. So you have about 10,000 synapses for each fixation you make. So you don't satisfy statistics 101 either. OK, so we trained this up on, or they trained it up on sound waves, trying to predict which piece of which phoneme was being said. So imagine a little bit of a spectrogram, which is essentially what the bottom is. And you're looking at this piece of the spectrogram and saying, in the middle of the spectrogram, which piece of which phoneme is this guy trying to say? And you get a probabilistic answer. And then you take all those probabilistic answers and you string them together with something else to find a plausible utterance. Nowadays, you don't do that. Nowadays, what you do is you just put sound waves in and you get the transcription out, and the only thing is a neural network. It's a recurrent neural network. But back then, this was just the front end of the system. We replaced the front end of speech recognizers with this, and it worked better. It worked just a little bit better. But good speech people, particularly Lee Deng at Microsoft, realized right away that if this works a little bit better, and 2 graduate students did it in a few months, it's going to completely wipe out the existing state of the art. And indeed, over the next couple of years, it did. So Navdeep Jaitley, a grad student at Toronto, he wanted to go to RIM and take this technology to RIM. He really wanted to do that, and I talked to RIM, and they said they weren't interested in speech recognition. I don't know what became of them. So by 2012, Google was using it in the Android, and that was the first time there was a big increase in speech recognition performance then. It suddenly got better than Siri. Now everybody's using this algorithm, but more updated versions of it. And all the best speech recognition systems are now trained with backpropagation in a neural net. And some are just end-to-end. In some of the systems, there's nothing else. You just train it on data. All that, how you pronounce things and what the words are and all that stuff, forget it. The net will learn all that. Then in 2012, 2 more graduate students of mine. So the trick to all this is you have to always get graduate students who are smarter than you. There's no point having a graduate student dumber than you, because you could have done that. So 2 other graduate students, Ilya Sutskova, who recently got given $1 billion by OpenAI to run a lab, which is slightly depressing because that's a lot more than I ever got. And Alex Krzyzewski, they took the ImageNet competition where there were 1 million images and 1,000 of each class, and you had to recognize the objects in that class. And it was a public competition with a secret test set, so you couldn't cheat. And the person who ran our system on the test set told me, I met him at a conference, he told me he didn't believe the results. So we went back and ran it again, and he still didn't believe the results. And he had to run it 3 times before he believed the performance results, because they were so much better than anybody else's. So here's the results. In 2012, all of the conventional computer vision systems that didn't use neural nets had plateaued at about 25% error rate. And our system almost halved that. And as with speech recognition, as soon as people switched, then you got thousands of smart graduate students and thousands of experienced developers and so on, making this work really well. And by 2015, we'd reached, on that data set, people had reached human levels. One hero called Andrew Karpathy actually did the task himself, which took a lot of time, and got 5% error. And now they're down below 3% error. And so it's 1/10 of the error rate of the computer vision systems now, of the previous computer vision systems. So this made a big impact. Partly because speech had worked already, but people thought that was a niche. And speech worked first because they were the guys who had big labeled data sets. When this worked, people got all excited. And it was very good for IP lawyers. OK. So these are examples of the kinds of images. And notice they're not images that have one nicely centered object in canonical viewpoint. Most of the cheat is missing. And the red bar is what the system thought was its best bet. It gets told it's right if in the top 5 bets it gets the right answer, because it's not always clear what the right answer is. But you'll notice the bullet train, it gets right, even though it's only a small fraction of the image. The hand glass, it gets wrong. It thinks it's scissors. If you look at the other things it thinks it might be a stethoscope or a frying pan. And you can see why it thinks that, and you can see that it needs glasses. But the point is, it's got the visual appearance of something. If you look at its wrong answers, they tell you more than looking at the right answers. Now I'm going to go on to recurrent nets. So these feed-forward nets were very good at recognizing a phoneme in speech and recognizing an object in an image. But for dealing with sequences, you want a recurrent net. And the kinds of recurrent nets people use now are based on work by Hochreiter and Schmidhuber in 1997 that I'm not going to explain. And I'm going to simplify them. I'm going to pretend to you these recurrent nets are simpler than they are, because you really don't want to. It would be nice if they were this simple, but they're not. OK. So here's how a recurrent net works. It has a bunch of input neurons, not just one like it shows here, but a bunch. And that's representing the data at a particular time. So it might represent a word in a sentence. It might represent an image in a video. That's the input. It has a bunch of hidden neurons. And these hidden neurons connect to themselves. So if you look at the second time slice here, the second column, and look at that middle unit, it's getting input. It'll get some input from the input to the system, which might be the video frame or the word. It'll also get input from the previous state of all the hidden neurons. So it's remembering and accumulating information. And you can train this same thing with backpropagation. What you do is you feed it the inputs, and the hidden units accumulate information. When you get to the end, you see if they can produce the right answer. And if they can't, you backpropagate information. So you just go backwards through all those arrows. And one thing you'll notice about those arrows is they form a directed acyclic graph. That is, you cannot go round in a circle following the arrows. And that means you can do backpropagation in it. You can go backwards without ever getting in a knot, basically. So, Ilya Sutskever and Oriol Williams and Kwok Lee, and pretty much in parallel, Yoshua Bengio and Bardanu and Cho in Montreal, developed a way of using these algorithms for doing machine translation. And initially it seemed crazy. So what we're going to do is we're going to have an encoder network that reads the sentence in one language and turns it into a thought. And then we're going to take the thought and we're going to turn it into a sentence in another language. Of course, to do that, you need to know what a thought is. Now, most people in AI, in fact, still most people in AI, they made a very naive mistake, which is they thought that strings of symbols come in, that's words, and when you say something, strings of symbols come out. So they think what's in between must be something like a string of symbols. That's as stupid as thinking pixels come in, and when you print something, pixels come out, so everything in between must be pixels. And in fact, the symbolic AI people were laughing at that view, that it's all pixels in between. That was a view of someone particularly naive called Steve Coslin, and they laughed at that. But they had exactly the same mistake. They thought the stuff that comes in and the stuff that comes out, which is the only stuff we know about from outside, it must be the same kind of stuff in the middle. Even though you know that what's in the brain is just big vectors of neural activity. There's no symbols in there. There's particularly no symbolic expressions in there, and there certainly aren't rules for manipulating symbolic expressions. At least after many years of high school, there might be a few of those rules that you can't really follow very well, but that's not the basic way of doing business. So you're going to put words into this encoder network one at a time. It's going to first turn those words into a vector representation, which is a whole bunch of features. And it's going to learn to do that. So all of these connections are learned by backpropagating. And it's going to basically make, say, the vector for Tuesday be very similar to the vector for Wednesday, and very different to the vector for although. The words come in, it accumulates information in its hidden units, and at the end of the English sentence, at the top there, there'll be a state of the hidden units that I will call a thought. And that's not meant to be a joke. That's what I believe a thought is. A thought is an activity pattern in a big bunch of neurons. And it's an activity pattern that doesn't need to be inspected for things to happen, it causes things to happen. So I can say to you, John thought, damn. Or John thought it's snowing outside. Anything you can put in quotes, John can think. And what's more, John can say it. So if John thought it's snowing outside, he might say to you, it's snowing outside. So it's obvious that the way you get at thoughts, the way I tell you what I'm thinking, is either by the words that would have caused the thought, or by the words that the thought would have caused. It's hooked up at both ends. But the thought itself doesn't look anything like words. It's something completely different inside. And in fact, it looks like that. It's not necessarily red. You take that thought vector, and you give it to a decoder network. And the decoder network says, OK, that was the thought. Let's suppose it's doing English to French. What's the first word in French? So it takes a thought and it says, OK, I think the first word is probably le, but it might be la, and it might be something else. It gives you probabilities of all the various words. One way of seeing what the network, one way of decoding the thought, not the best way, but one way to do it, is to say, OK, take those words it thought were reasonably possible, pick one of them according to how probable it thought they were, and then lie to the network. Tell it, OK, that was actually the right. You got that right. OK, what do you think comes next? And then it gives you a prediction for the next word. And you say, OK, you got that right. What do you think comes next? And that way, it will give you a string of words until it eventually gives you a full stop. And then that's the translation. Now, what's amazing is that actually works. That is, you train the whole thing with backpropagation. And Google Translate used to have huge tables of phrases. This phrase in English tends to go to that phrase in French. And you try and put all these tables together to get a plausible French sentence. And it turns out it works much better to have a system that has no linguistic knowledge whatsoever. That is, it's actually got lots of linguistic knowledge, but it wasn't put in by people. So now the way Google Translate works on many pairs of languages, and soon all of them, I think, is you take a language. You automatically break the words of that language into 32,000 fragments. So fragments for English would be whole words like the. There'd also be the individual letters. There'd be things like ing and ed and s. And you represent the input string by this string of symbols, these 32, drawn from this alphabet of 32,000 symbols. You feed it the English sentence. You have a big database of translations. It then produces the French sentence, and it has these probabilities of producing words, and you look at each point in time when it's producing the French sentence, you look at the probability it assigns to the correct word, and you say, I'm going to backpropagate through all those connections you see in the net there, send information backwards, computing how a small change in that connection strength would increase the probability of the right word. That's all you do. And so you start with random weights, and then you send all this information back to change the strengths very slightly so as to increase the probability of the correct word. And you do that for a lot of things. And hey presto, it's the best machine translation system there is, pretty much. One big improvement that was made by researchers in Montreal is attention. So the system I described to you turns English into a thought and then turns the thought into French. Of course, that's not what a real translator does. I mean, he could do that, but he'll do better if, as he's producing the French, he looks back at the English. And so they made their networks look back not at the input words in the English, but at the hidden states when it was getting English words. And they made it learn where to look. So that's pretty fancy. It's an extra module in the network that's trying to learn where to attend in the English sentence as it's producing the French sentence. And it successfully does that. And it makes the whole thing work better and be able to be trained on much less data. So that's one win. The word fragments I already described. Don't use words, use pieces of words. It'll also work if you use individual letters. In fact, here's an amazing thing. If you're translating Chinese to English, and I give you the following choice, you could have a big list of Chinese symbols, because they have symbols for whole words, or I could give you bitmaps of the Chinese symbols. Which would you rather have as input? Well, it turns out it works better if I give you the bitmaps, because backpropagation learns that Chinese symbols actually have componential structure. A Chinese symbol, you know, there's a man running to a house or something. I know nothing about Chinese, but those little bits in there actually have morphemic structure, and it'll learn that from bitmaps. So this is rather bad news for linguists. The number of linguists you need to make a really good speech recognition system is 0. Actually, that's entirely unfair. You need to have a well-curated data set, and linguists will know a lot about how to get a well-curated data set. But you don't need them telling the neural network what to do. Now let's combine that with the vision we did before. So we're going to take our net that recognizes objects in images, trained on ImageNet, and we're going to say, when we translate, we get a thought, and then we say that thought. Well, what if we got a percept, and then we said that percept? So instead of using English to get the thought, we're going to use the ImageNet thing to look at an image and get a thought, and then from that thought, we're going to produce the output. And the thought, or percept, that the net has is simply the activity of all the units just before the answer, the last hidden layer. Because what the net has done is really, it's turned pixels into activity of a bunch of things that's to do with objects, but to do with lots of objects in the image, and then it makes a choice and says the name of an object. But before it says the name of an object, it has stuff to do with lots of objects. So we use that percept as the encoding, and then we decode it. And we train it to decode. That is, obviously, percepts, to say those, you need some training. So you take that last layer of ImageNet, and you take a big database that Microsoft kindly supplied, with a few 100,000 images, each with several possible captions, and you train the decoder to turn that percept into a sentence. And then it does things like, you show it that, and it says, a group of people shopping in an outdoor market. The actual transcript of that is the correct answer, according to the database, is people are crouched around in an open market, which is better, because it's got the crouching and this hasn't. And then the one you saw at the beginning, so we reach closure. You now know how this worked. We trained up something on ImageNet. We then trained the output layer of that thing to produce sentences in English. And it says a close-up of a child holding a stuffed animal. The real caption, a young girl asleep on the sofa cuddling a stuffed bear, is somewhat better. But I was just completely blown away by this. When Oriol Vignals and Sami Benjo and other researchers at Google showed me that this worked, I thought, well, you know, that's the dream of AI, to be able to look at a picture and say what's in it. I mean, that's sort of basic AI. If you can do that, you're really onto something. And it worked. And then within about a week, lots of other people had done similar things. I think ours was just slightly better. There's all sorts of implications for document processing. If you can convert a sentence into a thought and then model the structure of those thoughts, you can get natural reasoning. You might not want natural reasoning because most people's natural reasoning isn't much good, but at least you can model it. I think to do this properly, we'll need a number of parameters comparable with the brain, which is 100 trillion, and our neural networks currently have a few billion. So there's a puzzle here, which is we can translate between multiple pairs of languages using a few billion weights. That's less than 1 voxel of a brain scan. So either the brain is amazingly much better than what we can do, or it's using a different algorithm, or it's using backpropagation but inefficiently, and I don't know which. In medical images, very soon we'll be better than radiologists. So already for skin cancers, there's a system that's comparable with radiologists, with dermatologists. And actually, as soon as it's trained on more images, it'll be significantly better. That was trained on of the order of 100,000 images. Train it on 10 million and it'll be better. One thing to bear in mind here that doctors often worry about is where do you get the correct answers? Well, here's something interesting. You train a neural network on labels produced by doctors, and the neural network can end up much better than the doctors. That is, the doctors all disagree, only have 70% agreement. The neural network actually gets what's going on, and it can be much better than the labels you use to train it. That seems paradoxical, but it's not. So we don't actually need the ground truth. We just need enough, something related enough to the ground truth so the neural network can figure out what's going on, which the doctor couldn't, and then we can do better. I want to finish with one story about the same student, George Dahl, as was involved in the speech recognition in 2009. In 2012, or 11, I think 12, he entered a competition on Kaggle, which he entered quite late. And the competition was, I give you a few thousand properties of molecules, and you have to predict whether this molecule will bind to something. The drug companies would like to know this, and they'd like to do it without synthesizing the molecule. So they'd like to predict which ones are good candidates for binding to something. George basically threw our standard neural network at it. Multiple layers of rectified linear units, far more parameters than there were training cases. Here he was using probably 1 million parameters with 15,000 training cases. And it worked. He combined it with other methods, but he didn't need to. It actually would have won the competition without being combined with other methods. And there was a prize. There was a $20,000 prize. And so George said, OK, give me the prize. And Merck said, well, it's part of the competition that you have to tell us what QSAR you used. And George said, what's QSAR? This is slightly embarrassing because there's a field called QSAR. QSAR is quantitative structure activity relationships. That is, how does a structure give rise to the activity? It's been going for like 20 years. It has a journal, it has an annual conference, it has a whole bunch of people who that's what they do. And George wiped them out without even knowing the name of the field. OK, that's it.